Hi, this is Mike, WA3TTS, and we're going to take a quick look at a 475 kilohertz diplexer. And this is simply a series resonant shunt that cancels out at 475 kilohertz. So this inductor's 50 ohms of reactance and this capacitor's 50 ohms of capacitive reactance at 475 kilohertz. And the same with these two. And what happens with the trap here is that it doesn't let the 475 kilohertz energy down through the trap, but all other frequencies do go that way through whatever reactance is presented to them here. So you got power coming in, and if it's way off of 475 kilohertz, it's going to run right through this capacitor and see a dead short to ground in 50 ohm load. And you got reflected power coming back. It's going to run through this inductor or capacitor same way if it's way off resonance and see basically a short to ground. So that'll take all that energy and get rid of it. But it'll pass the 475 kilohertz energy through this resonant circuit, series resonant. Okay, so if we look at this on the MFJ, I'm at 3 megahertz, which is 3.5. Let's go to 3. So that's 49 is R, real resistance, and X is 0. Let's see what the return loss is. .48 dB. Okay, now return loss, 20 dB of return loss is 1% reflected power. 30% or 30 dB of return loss is 0.1% reflected power. 40 dB is 0.01% reflected power, etc. Okay, so we have like a perfect match here at 3 megahertz. Now let's go down in frequency, and you see we're still down to 1.7. We're still a perfect match. All right, well, you expect that with that laboratory grade load there. Let's take the load off and see what happens. Let me set this down a second. There we go. Okay, so now I'm at go back to 3 megahertz. Now I've got 28 dB of return loss at 3 megahertz. Let's see where it hits 30. I got 30 dB of return loss at 3.3 megahertz. Okay, so I got 0.1% reflected power into an open circuit with this diplexer right now at 3.3 megahertz. Now let's take it down to 475 kilohertz and see what's going on. See, we have an open circuit now. We have a terrible match. We'd expect that. If we have an open circuit, we got like 0.2 dB of return loss. Let's put the load on it, represent what we would have. Okay. And bingo, we have 475 kilohertz. We have 24 dB of return loss. Okay, we know 20 dB of return loss is 1%, and we know an extra 3 dB would be half of that, so we got 1/2 of 1%, a little bit better than that for return loss in this situation with matched load, which is acceptable, really, really acceptable. Most ham radio antennas don't tune that well. You know, on a simple dipole, you might find one frequency where you have that match. So that's why these things are really, really useful. They present a matched load across a wide range of frequencies, so your mixer or your amplifier sees that characteristic impedance, in this case 50 ohms, you know. But if you had an amplifier with a different characteristic impedance, like say 4 or 8 ohms, like a Hafler amplifier that you wanted to use at LF, you could build a diplexer for that one as well on the input side, because these resistors requirements would get large with, you know, power output. But on a driver input, you might only need 1 watt resistors or 5 watt resistors or something on that order to use this circuit and take advantage of the great stability that it offers for any kind of mixer or amplifier arrangement at LF, MF, HF frequencies. Anyway, the neat thing to remember about this is when you design one of these things, there's no magic tricks here. These are just L is 50 ohms at the design frequency of inductive reactance, and C is 50 ohms of capacitive reactance at the design frequency, and they all kind of match out. Alright, so you might say to yourself, well, what kind of loss is going through this thing? I can show you that. We'll go over here. We'll turn this. There we go. My AC power switch is getting flaky on this. Let's take the diplexer off. And let's go to 475.123.0. Hit enter. Go here. We'll pick 50 ohms and no terminations. Okay, so I got 0.27, 0.28. Usually it takes a minute or so for this thing. I'm going to take this off. I'm going to let it recal again. It should come down to like 0.17 or 0.19. There it is. Okay. Do I have a quick way to get this back? No. Okay. Let's do this. Let's add this. Okay, now we've added a jumper cable, and we're up to 0.21, 0.22 insertion loss from the cable. Now let's put the diplexer in. So I got 0.25 versus 0.22. So I've got 0.03 dB of insertion loss at 475 kilohertz on this thing. And it's just a 61 ferrite inductor and you know, polyfilm or silver mica caps. There's no magic tricks here. And 50 ohm carbon resistors. Okay, let's go to like 3 megahertz and see. 123, 123.0. Okay, so it's 16 dB down. So I'm getting 16 dB of suppression at 3 megahertz versus 475 kilohertz. Let's go to 2 times 475, which is what, 950? Something close to that, I think. I don't multiply well in my brain. So we're 5 dB down for the second harmonic. Yeah, I'll take that. Along with, you know, 50 ohm match from DC to 30 megahertz. Let's go to 470. Let's go to 1325 would be the third. 1325123.0. Okay, so we got 8 dB at the third harmonic. It would be 1475. No, 4. 3 and 4 is 17. Let's go frequency 1775. Next harmonic, so there's over 10 dB, 11 dB there. So this is a great way to get some extra stability in your circuit. And it also, the other thing you can do with these is you can put them in a right after any kind of other low-pass filter, and they'll provide a 50 ohm reference for the filter, and they won't throw the filter way off like would happen if you try to take 2 low-pass filters and put them in series. They'll talk to each other and it won't work. But you can take a low-pass filter and tack this on the end of it and pick up that extra 50 ohm match across a broad range of frequencies and get several extra dB of isolation from your desired frequency range as well. So really neat circuit. It's really simple to think about if you just remember that these inductors and capacitors are merely 50 ohm reactants at the intended design frequency. So there's no real magic here. You can calculate these for any frequency range and throw a diplexer together and solve some problems. Anyway, I wanted to share that. I know a lot of people look at this and go, well, why do they do that? And that's why. It's the magic 50 ohm matching tool. 7-3 from WA3TTS.